Okay, guys, this is where we left off after problem 81 with problem 83, right? Let me read the problem to you, okay? It says a 3.5 liter gas sample at 20 degrees Celsius and a pressure of 86.7 kilopascals. Now, you don't realize that it is a combined gas law problem right away. You have to continue to read it. But that's what's given here first, correct? And you know that that's what you do right away. It should be reflex by now to convert it to Kelvin, correct? You don't have to take a lot of notes because everything is there done for you. You don't have to take notes. There's no reason to take notes. You want to pay attention and try to listen and understand it and actually comprehend what we're doing. Okay, and then when you continue reading, it says, this volume of gas, 3.5 liters, expands to 8 liters. The final pressure is 56.7 kilopascals. What's the final temperature of the gas in Celsius? So therefore, you see right away that there's a second set of conditions. If there's a second set of conditions, you know right away that it's combined gas law, correct? So they give you these conditions, and then they say, well, here are other conditions, and we want to know what the final temperature is going to be like in Celsius. What are all calculations done in temperature? Kelvin. So you're going to have to do the mathematics in Kelvin and then convert to Celsius, correct? So what we're going to do here is we're simply going to plug in PV over T equals PV over T. This is 1 and that's 2 sets of conditions, correct? So you're going to say 86.7. I'm leaving off the unit labels because you want to do a unit label check before you begin. Okay? Now, pressure is the same. The pressure could be in atmospheres. Why doesn't it matter? Because the atmospheres will cancel, correct? As long as they're the same, correct? When you're doing combined gas law problems, you want to make sure that everything's the same. The only one that has to be something specific is the temperature, because you can't do calculations unless it's in Kelvin. So that checks. Liters is fine because that's what you're also given. So temperature is going to be Kelvin, and then we're going to convert that to Celsius because that's what the problem says. So are all the unit labels correct? So then let's ignore them and just put in the numbers. Okay? So then you're going to say 3.5 for the volume over 293 equals 8. Let's do the pressure first, keep it consistent. Times 8 over T. How do you do this quickly? Well, you're going to multiply and divide and just keep multiplying and dividing. Okay, you can use parentheses or just keep hitting divided by. Let me explain. You ready? You're going to multiply 293. Do it with me. 293 times 56.7 times 8. Make sense? Divided by 86.7 divided by 3.5 equals. And you should get the answer of 438 Kelvin.
Yeah.
Correct? Yes? Let's do it a slightly different way. Okay? This is what the book will tell you. It'll say 293 times 56.7 times 8 divided by parentheses 86.7 times 3.5 and parentheses. So they'll have you do it that way. It's the same. If you don't use parentheses, you just have to hit divided by each time. Because I'm dividing by that, then I'm dividing by that. Easy? Yes? Okay. So I'm going to convert that to Celsius. I'm going to subtract 273, and what do you get? 165. That's the answer. Is that coming out on the film?
Yes.
Hassan, are you with me? Excellent. Excellent. Okay, are we done? All right, let's quickly go into 74. Okay, 74. Okay, which is 62, correct? Which is 62. So let me get literally on the same page. All right? All right, so it's going to be the rate of A over the rate of B equals the square root of the molar mass of B over the molar mass of A. Does that make sense? Yes or no?
Yeah.
Not exactly what I have on the PowerPoint, but close enough. Clear? All right, now, what do we say? What is the question? It says calculate the ratio of the velocity of helium atoms to the velocity of neon. So in other words, what's A going to be? This is going to be helium, and this is going to be neon. Correct?
Yeah.
So then this is going to be neon, and that's helium.
Yeah.
Correct? Yes or no? Is that easy? Yes? So you want this ratio to equal this. What is the only data we have? It's not really data. What do we have? What's the molar mass of neon?
20 grams.
What's the square root of 5? What's the square root of 5? 2.25-ish. Correct? I will give you a hint, and everyone at home. Are you ready for the hint?
Yeah.
Know this problem.
Okay.
Okay? Know this problem. Kaylee, how you doing back there? You're like right there. I like that. Everybody look at Kaylee quickly. She's right there. She's right with me. I like it. I like it.
Yeah.
Martha, I like it. The good group. Okay, now, so do we understand what we're doing there? Yes or no? Fatima, are you discussing the ins and outs of that problem, the finer points? Excellent.
Yeah.
Excellent. All right. All right, now, let's see. Let's see. What number are we doing now? So we did 83, 74, 81, 83. Let's do one more. Let's go completely crazy. We'll do 84, okay? It says, explain the reasons why real gases deviate from ideal gas behavior. Why do they deviate? Why do they deviate? We're just going to talk. We're just going to talk. Are you ready? Now, if I have, all right, I have ethyl alcohol. Do you know what that is? Like rubbing alcohol, isopropyl alcohol, ethyl alcohol. We're going to say ethyl alcohol though, right? Excuse me? Whatever. It's stinky, it smells, it can clear your sinuses, right? It's illegal to drink. If you're a certain age, you certainly don't want to drink the stuff you get in the pharmacy anyway. But is it a unique substance? I mean, if I gave you some ethyl alcohol, you could say to me, it might be ethyl alcohol, right? You could reasonably conclude that it might be, right? You'd obviously have to do some tests, right? But would you say that is water? No. Okay. Now I'm going to give you some water too. I'm going to give you ethyl alcohol and water. Okay? All right. Can you tell the difference between the two?
Yes.
Okay. Why?
Because that one is thicker than the other, the substance.
Water's thicker. I like that. And when we get to chapter 15, we'll understand why that's thicker. I like that though. Extra credit if you say that in chapter 15. It's thicker. I like that. I like that a lot. Okay. Now, so I can tell the difference between ethyl alcohol and water, correct? They're liquids, aren't they? The particles are close together, aren't they?
Yes.
The water molecules know, you could think of it in an imaginative way, you could think of it that if the water molecules could think, they know that they're all water molecules, right? And they know that in the water neighborhood, they know that they have a lot of neighbors who are also water molecules, correct? So all the molecules are close enough together. They live really right next door. They have a lot of land. They have about an acre each. They're not on top of each other like in an urban setting, but they have neighbors and they borrow sugar and butter from each other, right? They go fishing with each other. There's neighborhood cookouts, right? So they know that they're all water, correct? And they only hang around with water. Sometimes they'll be given visitors, like some ethyl alcohol will come in there, and they'll kind of like have like an a mixed party. Yeah, okay. Now the ethyl alcohol is in another neighborhood, and they know that they're all ethyl alcohol molecules, right? Correct? All right, good. Now a gas at room temperature, oxygen and hydrogen, are they close together? Are they? Are gas particles as close together as in a liquid?
No.
Remember I spoke to you about this. That means that the difference, the spacing, that's like potential energy, right? You're not increasing kinetic behavior because the temperature's not increasing, is it? That's temperature, right? This is time, right? So you could say that the liquid molecules are extremely spread out, aren't they? I'm sorry, the gas molecules are extremely spread out relative to the liquid molecules, just based on that one idea, that the potential energy is tremendous relative to the difference between liquid and solid. This is gas. So liquid gas, much farther apart than liquid solid, just by looking at the kinetic energy, the potential energy, wouldn't you say that's true? So is it reasonable to assume that the molecules of a gas are so far apart that they don't know each other? They're in different countries in like 3,000 years ago. Do the Greeks know about the American Indians? No. They don't know about the Native Americans, the Native North Americans, the Native South Americans, do they? They don't know about do the Native North Americans know about the Native Greeks? No, of course not. Do they pull out the television and see 300 and look at the Peloponnesian Wars and the Battle of Thermopylae? Can you see Geronimo sitting back, hanging out on his couch and saying, wow, that was a cool movie. I like those Greeks. Actually, Geronimo had a lot on the ball. He may have known about that. But anyway, yes? What is what?
Technically, the Native Americans might have known about the Greeks.
I'm sorry, technically what?
Technically, the Native Americans might have known about the Greeks because Native Americans first originated from Vikings that came over in about.
I'm not sure that's true, but let's say that for another day, that discussion. But anyway, the point is this. That the gases are so far apart that they don't know each other, do they? Matter of fact, Rashid, you can put oxygen molecules in with helium molecules, TJ, thank you for participating, in with fluorine molecules, and they don't know each other because they're so far apart. So they act in an ideal fashion, don't they? That's where the whole concept of ideal behavior comes from. Ideal behavior is not necessarily a theoretical model that's not based on real life. Ideal behavior does exist, but within a pretty small, narrow field of conditions. Yes? In other words, if I take ideal gases, if I take a mixture of hydrogen, oxygen, chlorine, bromine, and iodine, and I mix them at room temperature, they're all going to respond the same, correct? At room temperature. If I take a mole of chlorine gas at STP, it's going to be 22.4 liters. That's real, that's true. If I take a mole of oxygen, hydrogen, chlorine, fluorine, bromine, iodine at 0 degrees Celsius, and they're gaseous, they're all going to have the same volume, aren't they, in one atmosphere, right? Yes or no?
Yes.
Because they're so far apart, they don't know the difference. They don't know each other. They don't have barbecues. They don't hang out. They don't go fishing. Largemouth bass fishing, excellent stuff, man. I love it. Down in Georgia, oh, it's lovely. Yes? Little bass boat, brilliant. Now, but if I increase the pressure on those gases, what am I doing to the distance between the molecules as I compress those gases to many, many hundreds of atmospheres of pressure? What am I doing to the proximity of each gas molecule relative to each other gas molecule? All of a sudden, the gases start to respond in a unique manner because they're getting close to each other, right? So they're starting to act real. What do I mean by real? Like as opposed to fake? No. In a sense, you're the example I started with, water and ethyl alcohol. They're real because they have unique identities. I can tell the difference in many ways. But if I had oxygen and nitrogen at STP, and I'm seeing if there's going to be a different volume based on those conditions, there's not going to be. They're going to have the same volume. Yeah? If I do the same experiment with water and alcohol, I'll have different volumes because they expand differently, right? They expand differently. So let's not say real and ideal. Let's say unique and general. Unique and ideal. Right? So when do ideal gases start to lose that generic behavior? When do they start acting like individual gases, where chlorine will act like chlorine? In many ways, as opposed to oxygen, where I can tell the difference. At what conditions? At high what? High pressures, yeah. High temperatures, high pressure. They'll start to act in a unique manner. Yes, obviously, nitrogen and oxygen, if I'm breathing, I can tell the difference between oxygen and nitrogen. That's not what I'm talking about. They're like chemical differences. But physically, they're very similar. I'm talking about the physical, not whether or not they react chemically differently. Correct? Why do we study gas laws? Why do we do that? Why do we do that? Why do we study the environment? Why do we study atmospheric pressure? Why do we do that? Because chemical reactions occur differently at different physical conditions. So you have to study physics when you're studying chemistry. You have to study gas laws. Gas laws is physics. But when I teach physics, we don't call them the gas laws. You know what we say? We say fluid statics and fluid dynamics. Because gases are fluids, yeah, anything that flows. So we don't really say, I honestly don't say gas laws. When I talk about Bernoulli's principle, we talk about fluids because the properties of many fluids, they're all the same. Gas or liquid, they're the same. Yeah, sure, we study gas laws, yes. But we study them in the context of fluids, where we're studying gases and liquids apart from solids. Enough said? You get it? Yeah. Ideal versus gas. And you can look at graphs. As you increase the pressures, you can look at the fluctuation of ideal behavior as you increase the pressures. Yes or no? Yes. Absolutely. We're done.